No problem. So, okay, so here we are on the Atlantic layer, and this layer of water of Atlantic origin, it's somewhere like 0 to 4 degrees centigrade, depending on the location and the season, which may not sound like really hot and balmy if you're looking for a place to swim. But the point is that it's warmer than the surface waters, which are typically more like -2 degrees centigrade near the freezing point of the ocean. And it's estimated that there's enough heat stored in this Atlantic water layer to melt the sea ice many times over if it mixed up to the surface. And that idea has gotten a lot of attention. But this Atlantic water layer is isolated from the surface by a stable halocline layer where the salinity in blue here changes rapidly with depth, leading to a strong stratification. But recent observations have found increasing upward heat transport across the halocline, at least in some parts of the Arctic Ocean, which raises the possibility that as the sea ice recedes, we might be mixing, the level of mixing across the halocline might be going up. I'll say more about that later, but here's the outline of what we'll talk about. First, looking at spots, locations where sea ice remains during global warming, and the mixing then stays approximately constant. And then the second part of the talk, we'll look at locations where that lose sea ice as the globe warms, and the possibility that mixing there would increase, and what the implications are of that. Okay, so we'll start with constant mixing. And I want to start with sort of simplest conceptual picture I can of what things would look like and what are the implications of having this interesting situation in the Arctic where there's cold water near the surface and warm water at depth. So what I've sketched here very roughly is sort of characteristic temperatures for the midwinter season in the central Arctic near the surface, right around the freezing point with sea ice above at something like -30 centigrade. And then a few hundred meters below the Atlantic water in the central Arctic being a couple degrees centigrade. And then to include heat transport, horizontal heat transport from lower latitudes, I've added a couple other boxes here for a subpolar region, which I've taken to be 3 degrees centigrade near the surface and at depth. And it turns out in a simple picture like this, something really interesting can happen when we do global warming. So, oh, I got ahead of myself. First off, I should say, heat normally moves from hotter places to colder places. And so here in the Arctic, the heat's moving upward from the deep Arctic, deep ocean up to near the surface ocean, which is consistent with observations. And then in this picture, we also have heat moving poleward at depth from subpolar to polar in the deep boxes, also going down gradient from a warmer location to a colder location. But as I was saying, something really interesting can happen here when we do global warming. So imagine we do like a real simple global warming, keeping with the simplicity of this 4-box picture. So we have a globally uniform increase in radiative forcing, and basically everywhere warms by, say, 3 degrees centigrade. But the thing is, there's one box that can't warm here, and it's this one, because we still have in locations where if we do a small enough global warming that there's still sea ice in the central Arctic, then there's still a phase change between ice, liquid water, and solid ice, which means that the water here has to stay right at the freezing point for salt water, around -2 degrees centigrade. And so every box warms up by something like 3 degrees centigrade, except for when you're underneath the sea ice. And that box remains fixed, which means that the vertical temperature gradient in the central Arctic gets bigger, which implies, all other things being equal, more upward heat transport. So if we put more upward heat transport into the near surface or surface layer in the central Arctic, that heat needs to go out upward through the top. And to get that, the surface temperature has to warm. Now we're pumping all this heat out of the deep central Arctic layer, and that's going to cool. And it's going to cool until the meridional temperature gradient is big enough so that this heat flux and this heat flux both balance. So what this implies is that, at least in the simplest picture, if we have regions that maintain sea ice during global warming, there should be an increase in the ocean heat transport into those regions and an increase in the upward heat flux to the surface in those regions, leading to a warmer surface, which could be relevant to Arctic amplification of global warming, the phenomenon that in both observations and in climate models, typically global warming is amplified strongest in the Arctic. The reasons for Arctic amplification are typically discussed in terms of atmospheric processes and radiative feedbacks, like surface albedo, lapse rate, and water vapor. But this simple conceptual sketch implies that a basic mechanism by which ocean heat fluxes would also contribute to this. And so what we tried to do is make the simplest model we could that would include all the physics for this mechanism and pretty much nothing else. This is a schematic of the model. And here's the main model equations. So what this model does is it simulates the surface temperature, sea ice thickness, and the temperature of a subsurface layer, a deeper layer, as a function of time and of latitude, going from the equator to the pole. And the model has a seasonal cycle, and it includes sea ice thermodynamic processes and the ice albedo feedback. Briefly, the surface temperature evolves due to first a solar forcing, which is bright at the equator, smaller at the pole, and varies seasonally. Then there's an outgoing long wave radiation, horizontal heat flux in the surface layer, which is parameterized rather crudely as just diffusion of the surface temperature. And that's a common convention in these models, going back to the classic Boudico-Sellers style energy balance models, EBMs. Then there's also a specified forcing. And then lastly, we've added here a vertical heat flux between the two layers, which is just proportional to the difference in temperature between the layers. Meanwhile, the deep layer temperature evolves on the one hand due to that vertical heat flux, and then on the other hand, wanted to represent how heat moves from hot places to cold places, which we needed based on those conceptual boxes I sketched. And so we rather crudely just parameterized the horizontal heat transport in the deep layer as diffusion of the deep layer temperature, which neglects the structure of currents in the deep ocean, but hopefully gets at the basic features of this. And this model is based on one that we developed earlier in my group that I think Jake will have a variant of in his talk, maybe not. Okay, he has before, but now we're adding a deeper layer to it. So we run the model, tune the parameters, and this is a comparison of the simulated state in the model, surface temperature, deep layer temperature, and sea ice thickness. And here's estimates of those in the observations. You can see they're broadly consistent. The deep layer doesn't look very good it looks pretty good in the polar region, but not as good outside the polar region, where we've neglected a lot of processes like ocean gyres, et cetera, and it doesn't do quite as well. And next, we take the model and we just apply a radiative forcing. We hit it with a few watts per meter squared, globally uniform, to warm the model. What the model does is it warms everywhere, but it has an Arctic amplification. It warms more near the 90 degrees north here, near the pole, and less near the equator. And then next, we want to assess the importance of this proposed mechanism. And so to do that, we've just taken and locked the vertical heat fluxes. And what I mean is, normally in this model, the vertical heat flux is computed based on the difference in temperature between the deep layer and the surface layer at each location, right, at each latitude. And instead, we took the control climate and saved out of that what the simulated vertical heat flux was as a function of latitude and season. And then we just specify that back into the model to inactivate any feedbacks between the two layers. And what that does is it turns off this mechanism. Okay, and we tried warming the model when we locked the vertical heat flux, and that's in red. Here in blue is what happened when we warmed the model and we allowed that vertical heat flux to be interactive. And what that implies is this mechanism drives something like 20% of the polar amplification in this model. So it's not a negligible contribution. Okay, next, we compared this with GCMs. First, there's an interesting study a few years ago where the team took a GCM and they locked the ocean heat transport and warmed the model, compared that with a run where they didn't, so the slab ocean. And the results suggested that ocean heat transport drives something like 23% of the Arctic amplification in their model, which is similar to the result that we found with the idealized model. And then second, it's long been known that GCMs tend to simulate an increase in ocean heat transport around 70 degrees north under global warming. And the idealized model results give a similar increase in meridional heat transport, as we saw also when I just had those 4 boxes and the arrows between them. And that happens in the idealized model just due to this mechanism alone. So we're proposing then that this mechanism might explain the behavior in the GCMs. Okay, so let me recap this first part of the talk. So at least in this idealized world that we're looking at, the vertical temperature gradient in the Arctic Ocean increases under global warming. And this increase leads to then an increase in upward heat flux in the Arctic Ocean and an increase in poleward heat transport to supply that heat. And we're suggesting that contributes to Arctic amplification. Importantly, this mechanism only heats regions that remain ice covered during the period of global warming that you're looking at. And that's in contrast to something like the albedo feedback, which warms regions that become ice free under global warming. Okay, so part 1, we were asking what happens when where mixing stays constant in locations that maintain a sea ice cover during global warming. And we're suggesting here that there's a previously unrecognized basic thermodynamic process by which ocean heat fluxes amplify warming where sea ice is present. And there's a quick overview of it, but there's further details of this in a paper in Geophysical Research Letters. Moving on then to part 2, now we want to turn, instead of looking at the spots, locations that stayed ice covered during global warming, we want to ask, what about spots that become ice free during global warming? And what happens if the vertical mixing increases in those spots as the sea ice recedes? And so for starters, let's look a little more at the observations that motivate this. So the Arctic Ocean is characterized by low levels of vertical mixing, and that's attributed to a number of factors, including sea ice damping wind-generated internal waves in the upper ocean. Consistent with that, observations have shown that internal wave amplitudes in the Arctic Ocean tend to be considerably larger in regions that are ice-free compared to the regions that are ice-covered. Although I should note that the observations are somewhat equivocal on this point, and there's some debate about whether that applies everywhere or maybe just in the Eurasian basin. Okay, so what that implies then is that when we remove the sea ice and it no longer damps these wind-generated internal waves, the mixing would be expected to increase as the sea ice retreats. And that's been suggested in a number of papers, and consistent with this, as I mentioned earlier, vertical heat fluxes in the Arctic Ocean have been found to increase during recent years. So I think that this raises the intriguing possibility that we'd have a positive feedback loop and a kind of an interesting and novel one, where the sea ice melts, and then the sea ice is no longer there to damp these wind-generated internal waves. And so there's more mixing in the ocean. And that leads then to more sea ice melt by mixing up more of this heat in the deep Arctic Ocean. So we call this the wind ice ocean feedback. And then the thing we want to look into is it plausible that this could give rise to some rich nonlinear behavior in the Arctic, where we might even get bistability and like bifurcations, tipping points, hysteresis, all those things tend to walk hand in hand. You either get all of them or none of them. Okay, so for part 2 here, we're going to follow the same recipe we did for part 1. Start out with the same conceptual picture. Here's typical midwinter temperatures of the upper Arctic Ocean, deep sub-Atlantic layer of the Arctic Ocean, and then subpolar boxes. And now we're interested in whether whether we can plausibly get bistability due to wind ice ocean feedback. And so what I want to consider is what happens if we just do a perturbation to the surface ocean and just warm the surface ocean, not global warming, but just hit it with a momentary perturbation to make it hotter. I mean, -1 degree centigrade, but no sea ice. So all I've done here is warmed up the surface in the Arctic. But now if we warmed it up enough that there's no sea ice, that means there's no more sea ice to damp these wind-driven internal waves, which means that there's going to be a larger upward heat flux in the Arctic Ocean just due to more mixing in the ocean, despite a slightly smaller vertical temperature gradient, just because of if we can get a lot more vertical mixing to happen there. And if that happens, well, we're going to pull a lot of heat out of this layer. Whoops, this layer gets a little pull heat out of this layer. It gets a little colder, and then there's a little increase in the heat transport this way. And now we actually have a consistent picture where the energy is balanced, at least in this simple conceptual picture. And by having a wind ice ocean feedback, we can actually get bistability under the same forcing, depending on the initial conditions. We can have a warm state and a cold state. And one thing that's striking about this is I'm calling this the warm state because it has a warmer surface temperature, but the warm state actually has a colder deep Arctic Ocean than the cold state does. And that's I'd say a striking signature of this bistability, if we see it, is that the state with a warmer surface climate would have a colder subsurface ocean because more heat's getting mixed out of that deep Arctic Ocean. Okay, so similar to what we did last time, we're going to develop a somewhat more complete physical model to investigate the possibilities. We want, again, to include all the relevant physical processes for this feedback and ideally pretty much nothing else. So this actually, the model is a lot simpler than what we needed in the last part. We don't need any details of phase change at the surface. We don't need any sea ice thermodynamic processes, and we don't need a seasonal cycle or even an albedo feedback. And so this is an annual mean model, and it evolves the surface temperature just due to annual mean solar radiation. Again, the same alkaline long wave radiation, horizontal heat transport, and a vertical heat flux that's parameterized as the difference between the two layers. Specified forcing if we want to add it. The deep layer looks similar, just no seasonal cycle now, but a horizontal heat transport and that same vertical flux. The only nonlinear in this model, the thing we really want to focus on here, is this wind ice ocean feedback. And so what we've done is we've said this vertical mixing coefficient is going to depend on the surface temperature, and it's going to jump between a big value where the surface has a temperature above the freezing point to a smaller value where the surface temperature is below the freezing point. That's the only way that this model, it's the only place that the freezing point shows up in this model. There's no other physics of ice that appear in it. It turns out this model is simple enough. We can solve for the steady state analytically using Legendre polynomials, following on a sort of old convention in energy balance models. And then we also solve the model numerically to look at the time evolution. Okay, again, following what we did in part one, we'll compare the model with observations, and we find we can tune the parameters and get some values that look pretty similar to the observations. The model here is in red and the observations are in black. And you can see here, we're including the vertical heat flux, which has a discontinuity in the model where the surface temperature crosses below the freezing point right here. Although the results are going to depend on the parameters, and kind of unsurprisingly, because we're pretty generous about matching the observations, there are a lot of parameter sets that we could put in that arguably have a decent match to the observations. And then more than that, if you think about it, this idealized conceptual model probably has a lot of different processes that it's omitting that essentially have compensating errors. And so it's not obvious that the parameter set that we choose, which gives the best match to observed temperature fields in the surface and the deep layer, is the one that's going to give the most realistic behavior. But with that in mind, we took the model and tested it to see whether if we warm it up and cool it off, whether there's any bistability. And we tried this in a number of different parameter regimes. Okay, so here's the result. In the default parameters, the parameters that like most closely match the observations, there's absolutely no hysteresis whatsoever in the model. So in red here, we ramped it up, warmed the climate up. This is the sea ice edge latitude versus how much we heated it, specified radiative forcing. And then in blue, we cooled it down again. But there are parameter regimes where we totally get bistability and hysteresis and all that, just as we expected based on those 4 boxes with the arrows that I showed earlier. And this is an example of one of those parameter regimes. So you can see here, let's see, in black is the steady state stable analytical solution. The black dashed line is the analytical solution, the unstable solution to the model according to our analytical solution. This is the unstable state. Black is a stable state. There's another black line under the blue right here. Red is what is the time evolving numerical simulation when we warm the model up. Blue when we cool it down. And you can see in this parameter regime, there totally is a bifurcation, a tipping point right here as we warm the climate, where right past that, we abruptly lose all the sea ice cover. The Arctic becomes ice-free. And there's bistability here for certain values of the forcing parameter, like 5.5 watts per meter squared. It supports both a warm state and a cold state, depending on the initial conditions. I've just sketched here plotted the surface temperatures of the warm and cold state, and then the deep layer temperatures of the warm and cold state. And one thing to note here is that this totally has, as we saw from the conceptual picture with the boxes, the warm state right here in red has a colder temperature at depth in the Arctic. So now we're no longer just having 4 boxes, but having something that's essentially continuous in latitude. We made a whole lot of, I don't remember, a couple of hundred grid boxes in latitude. But in the central Arctic, the state that's warm at the surface is cold at depth. Another thing to note here, although it's a little harder to see, is that the surface temperature, the global mean surface temperature of both of these states is actually the same. I can see it better on my computer screen, but the blue is a little bit above the red for a lot of this. Keep in mind converging meridian. So this isn't, whoops, that's not that big an area of the globe. And that's because this is not a radiative feedback that causes this bistability, but it's a heat transport. It's an internal heat flux feedback in the climate system. And so what that means is that both of these states need to have the same absorbed solar radiation and the same, yes, oh, that's 5 minutes, and the same alkaline long wave radiation, which in this model means they both have the same global mean surface temperature. And that's in contrast to any bistability that would be brought on by radiative feedbacks, like, for example, the ice albedo feedback. So I'm doing well with time, ready to summarize the second part of this. So we were asking what happens in locations where sea ice recedes, and what happens if the mixing increases in those locations. And what we find is what I think is a pretty novel hysteresis and associated tipping point that can occur in the model, but only for a limited range of parameters. And we're not at all certain whether this would be likely to occur in the real world or not. And more details of that are available in a manuscript I'd be happy to send to anyone that we've submitted to what I'm sure will be a nasty ride through peer review. So with that, I think I have plenty of time for questions, probably. Thank you.
Yeah, thank you, Ian. We've got time for a few questions. I think Celia.
Can you say something about the limited range of parameters that gave rise to this bifurcation?
I can. Somewhere here. Okay. This is a plot. It's a lot like a plot that my group produced previously to try to shoot down the idea that ice albedo feedback would give bistability. But this is looking at this mechanism. This is what we call the default parameters right here. We're looking at surface diffusivity and deep layer diffusivity, which are two parameters that it's easy to explain why, but they're two parameters that matter a lot. I think the three parameters that matter the most is that and how big the jump is in the vertical coefficient as it goes ice-free. This is the parameters that most closely match the observations. This is what I showed otherwise. In terms of the surface diffusivity, there's been a lot of values that have been used in EBMs. I don't know if those, I mean, those are just based on matching the meridional temperature profile to observations, but this is numbers that were used for that value in 4 different studies. Deep layer diffusivity, it's less clear what parameters to use, but I think this gives some sense, like a lot of uncertainty in what would be the proper value for the surface diffusivity, but even more for the deep diffusivity. I think there's a lot of work to do to try and figure out whether this has any relevance. And is there any bistability that you might see in the real world? And even if there's not, is this relevant to help explain what happens in the real world? Ray has a question.
Just a quick one, like when ice melt, it gets fresher, and when it gets fresher, the K goes down because it gets much more stratified. So when heat comes into the Arctic, there's a branch that comes out, and so one could argue that none of it will go up, and all of it might just go around and come back out. And in the Canada Basin, from Ajax to ITP, this is certainly what we see. Like the increased stratification by far outweighs the increased vertical mixing. So it's one thing in the model that's missing. It's the K dependence on salinity.
I think you raise a number of important points. So one thing is, in my broad brushstrokes, I didn't really talk about different basins, but this whole story would be far more relevant based on observations in the Eurasian Basin than in the Canada Basin. I think if the Canada Basin's all you have, you can shoot this down pretty readily, and in the Eurasian Basin, there is a lot more evidence for this. In terms of the melt of the sea ice, I mean, we're looking at long-term stuff. And so if the climate slowly warms, additional fresh water from getting the thinning of the sea ice is kind of irrelevant because it's happening. You know what I mean? Imagine 2 equilibrium states, one before global warming and one afterwards. But there's also reason to think that the stratification in the whole basin would go up, and it does in a lot of models, just because the hydrological cycle gets more active. So there's, at least that's our reason for it. There's more rain coming into the catchment basin, and there's more stratification, and that would be competing with this.
Okay, we've time for one more question.
Hi, Ian. So box
Great.
models, I think, can be very instructive. But just thinking about your modeling there, it seems sensible to use diffusivity in the vertical direction. It seems much less reasonable to use it in the horizontal direction when you're thinking about these global scales. I would expect the heat transfer to be mostly advective. So have you thought at all about trying to parameterize the overturning circulation? I mean, a very simple way, because as you change the sea ice production in the high latitudes, you're going to change the strength of that circulation, change of your poleward heat transport.
Yeah, it's an excellent point. It's definitely very crude what we've done, putting in. I mean, diffusion, advection. I guess with the model, when we have diffusion, we can think of it as if there's a bunch of random currents that are advecting the heat. That looks like Brownian motion, that'll look like diffusion. And when we have a structured large-scale current advecting the heat, like an overturning circulation, it doesn't anymore. It looks quite a bit different. And we have thought about it. I think it would be really interesting. It's subtle what happens with, like, you mentioned that as the globe warms, the meridional overturning circulation gets weaker. And you can see that really nicely in this plot here from a bunch of GCMs. The meridional overturning circulation gets weaker as the globe warms, and as a result, there's less forward heat transport happening in mid-latitudes. But then this intriguing thing that we're trying to explain, that there's more forward heat transport happening nonetheless even as the meridional overturning circulation gets weaker in these high latitudes. We're proposing this mechanism for it. To explain that, I didn't say a lot about it. But yes, I would love to chat more if you have thoughts about it. And we've tried thinking about what's one level sort of more complicated here, maybe specifying some sort of an advective flow to move the heat around instead.
Thank you, Ian. Questions. Okay. So yeah, up next we've got Jake Elmer speaking.